What do you think of this figure here? Yeah. Is that accurate today? No. So unfortunately, a lot of people think that orbits are still valid. Orbits have long since been abandoned. Orbits have been replaced with orbitals, but you see orbits everywhere. I mean, people still conceptually think it's correct, but it's not. When we look at the periodic table, you know, different elements want to do different things. For example, oxygen. Oxygen wants electrons or loses electrons? Oxygen wants electrons. It wants 2 electrons to fill its shell. You know, so over here on the right side we have the oxidizers. On the left side we have the producers. You know, it's easier to lose electrons to end up with a closed shell versus gain. Over here we want to gain, over here we want to lose. Well, let's try out, let's try to do the electron configuration for neodymium. Neodymium here, neodymium is used in powerful magnets, electric motor magnets. Neodymium is element number 60. What is the electron configuration for neodymium? First. Neodymium is what we call a rare earth element. This is correct here. The rare earths. And we have the actinides. We have the heavy metals. There. Let's take a look. This is what the periodic table looks like in class. Here's neodymium, element number 60. Element number 60 means how many electrons does it have? 60 electrons. So what we can do is we can work backwards to the nearest double gas electron configuration, which would be xenon. Xenon, if we fill the first shell, second shell, third shell, fourth shell, fifth shell, if we fill the fifth shell, we're at 54 electrons. So we'll use xenon. It's only 6 more electrons we have to place. So we go xenon, and then this would be 6s1, 6s2, 5d1, 5d2. But take a look at what happens to the number. We go from 57 to 72. There's a problem with that. And so this is another one of the exceptions. This is not an exception you have to memorize because this is an exception we can get from the periodic table. When we get to these, what happens to the spacing? As we get higher and higher up, what happens to the spacing between the orbitals? They get closer and closer together, so you expect a lot more exceptions to happen at higher energy. Well, this is one of them. And so electron number 55, 6s1. Electron number 56, 6s2. Electron number 57, 5d1. But where does electron number 58 go? If we look, it goes down here. Do you see the star? Star. So electron number 58 is? No. This is not 5. This would be 5d2. This is actually 4f. And so now we're getting into the f orbital. So this is what it looks like here. Neodymium, we filled up to krypton here, which is 54 electrons, so we'll just save that. And so the next orbital is 6s2. And then after 6s2 comes what? So that's 54 electrons. This is 55, 56. After 6s2 comes what? Well, there's 2 ways of figuring it out. One is if you have the periodic table. The other is just to go like this: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 6s, 6p, 6d, 6f, 6g. What comes after 6g? 6h. And so we just go like this. Okay, so we're at 6s. So what comes after 6s? 4f comes after, and then, yeah. And so what comes after this is going to be, well, if this is L0, then L equals 1 is the P, L equals 2 is the D, L equals 3 would be the F. So I'm going to put in my 4F over here. Now, how many orbitals are in the 4F? Well, it goes S, P, D, F. S is 0, P is 1, D is 2, F is 3. So now we're at the 4F orbitals. Let's label them. It's going to be, the first one is going to be a 4, what? It's 4, and then we'll go to L. L is 3. So this is a 4, 3. 4, 3. Not -4. Here, when L is equal, M is equal to, we go from -0 to 0, so it's only 0. When L is equal to 1, we go from -1 to +1. So what are the M values here? -1, 0, and 1. When L is equal to 2, then the M values are going to be -2, -1, 0, 1, 2. When L is equal to 3, what are the M values? -3. And so the first one will be 4, 3, -3. What comes next? The next one will be 4, 3, -2, followed by 4, 3, -1, followed by 4, 3, 0. Yeah. 4, 3, 0, followed by 4, 3, 1, 4, 3, 2, 4, 3, 3. So how many orbitals is that total? 7. There's 7 orbitals here total. 7 orbitals. And the 4 7 orbitals can hold a maximum of how many electrons? 14. So there are actually 14. Are there 14 columns here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Each element corresponds to adding an additional electron and proton. That's 14. So this feels weird. And so what's going to happen is it goes like this. It goes to 6s to 4f, and then after 4f comes 5d. And so the 5ds are going to be here. And how many 5d orbitals are there? There's 5 5d orbitals. What are they? Well, they're the 5, 2, -2, 5, 2, -1, 5, 2, 0, 5, 2, 1, and 5, 2, 2. That's what they are. After the 5d come the 6p. And what are they? Well, there's the 6, 1, -1, 6, 1, 0, 6, 1, 1. And then that fills that shell. And so the 6th shell consists of this. The 6th shell consists of the 6s2, or the 6s, the 4f. That takes us to 71. Where's 72? 72 is back here. 5d to the 6p. And then we fill that shell. And we're at Rn. Rn is radon. radon is radioactive. So it's different than the other one. And so what we do is we just use the periodic table to tell us, to guide us. Periodic table will guide us through this. So it's going to guide us. It's going to tell us 56 is here, 57 goes here. And so 57th electron is in what set of orbitals? 56th electron, 57th electron goes, no, goes into this block is the 5D. You see 57 is in the 5D. Yeah, we can. Where does the 58th electron go? In the 4F. So the 58th electron goes here. 59th electron goes 4F. And then the 60th electron goes 4F. So this has a very weird electron configuration. It would be krypton 6s2, 4f3, 5d, 1. So this is another one of the exceptions. This is based on, there are two styles of periodic table. Let me just end with this. There are two styles of periodic table. Look at this one carefully, and then look at this one. Look at this one, and then look at this one. This one versus this one. Do you see the difference? So let's do it again. Let's do neodymium one more time. We're going to start with xenon, 54. And then we go 55th electron, 6s1, 56, 6s2. Where's the 57th electron? 57th electron looks like it's in the 4f. But very, very tricky, because look at what happened to the 5d. There's an element missing out of the 5d. If this were 4f, how many blocks should there be? How many electrons does the 4f accept? 14. So let's count the blocks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Very tricky. Very tricky. You know what that means? That this lanthanum actually belongs here. And so it's 6s2, 5d1, 4f starts here, the second. I don't know. I don't know, but anyway, I'll stop there. To confuse people.